So yesterday we talked about patterns of natural selection and how this occurred, and how would this cause the population to change over time. We also discussed some examples or of some relationships that would actually affect natural selection and affect the population. Today, before you start with your new notes on Unit 7.5, I do want you to take a little time and look at some of the links that are connected here on different examples of natural selection on the Endler fish and with tuberculosis. Also take some time to do the review questions and to look at these and use your textbook as a resource. But today our focus is going to be on measuring evolutionary change. And this is going to be technically section 7.5 of our notes. And we're really going to focus on evolution by using the Hardy-Weinburg laws and equation. So basically what we're looking at is this main question here. How do we know if a population is changing over time? And when we're talking about evolution, we're going to be talking about time in terms of generations. So the first thing that we need to look at when we're trying to study evolution by using this Hardy-Weinburg equation is by actually looking at the phenotype. A phenotype is caused by a genotype, which means really that the phenotype and the genotype are inherited characteristics. So we're going to try to determine whether or not evolution has occurred by looking at phenotypes and genotypes, by looking at those ratios, those frequencies, and that's going to allow us to say with some mathematical data whether or not evolution has occurred. So the first thing we have here are some terms and some variables that we need to know. First is the gene pool. The gene pool is just going to represent all the genes possible, or all the, alleles possible in a population, and the quantity of those alleles. Then you have this idea of allelic frequency, and this is kind of falling below your gene pool. The allelic frequency is really how often or what quantity of each allele is present in your population. Okay, so your gene pool is all of those alleles, and your allelic frequency is specifically what amount of each allele do you have. One of the key equations that we have to work with first, or have to understand first, is this P plus Q equals 1. So several different parts here. P is going to stand for our dominant allele. Q, therefore, is going to represent our recessive allele. And the 1 is going to represent 100% or all of the alleles, which means P and Q. So what are P and Q? P and Q represent phenotypes. So how do things look? Okay. P might be our light-colored moth. Q might be our dark-colored moth. Remember that phenotypes are physical trait or looks. What did your genes actually give you? How does that look in you? physically. Keeping this equation in mind, just saying basically this is giving us a percent of our dominant allele and the percent of our recessive allele in a population. And the percent of dominant and the percent of recessive should equal 100. So then we have to look at the second equation, and this equation is where it gets a little more complicated. And this is actually when we look at, these are going to be our possible genotypes. So, first thing that you have to see in this equation is that you have p squared. And actually, let's kind of switch what I said earlier. Let's say that p is the dark moths, and q represents the light-colored moths. If p and q are phenotypes, then all I have to look at is the percent of dark total plus the percent of white total. And this would give me 100% of my moths and 100% of the phenotypes that are there in the population. When you look at this next equation, this is looking at the genotypes that produce those phenotypes. So make sure you take a minute and look back and review that if you don't remember right away what I'm talking about. But here you have p squared, and p squared represents your homozygous, dominant, allele. PQ is going to represent your heterozygous genes that you received, which could be a big A, little a, or little a, big A. Just keeping in mind that it really doesn't matter which way you write it, but that's what it represents. Therefore, homozygous dominant would be big A, big A. And then Q squared, you've probably figured out, this is going to be your homozygous recessive alleles or genes. Okay, which is little a, little a. Notice in this case that little a does produce our small or light colored moth. So let's go ahead and get a little practice with this. You should be able to look at this image, and from this image determine what are our P and Q, what would that equal to, and then also look at our P squared, 2P squared, 2PQ, and Q squared, and actually be able to determine that looking at the numbers that they're providing you with here. At the bottom is an example, and so in this example it says a population has a percentage of the homozygous recessive genotypes, little a, which is 36%. Using that 36%, calculate the following. Pause the video. Take a minute to work out this problem on your own first. Do it in pencil if you're not sure, but pause and try this on your own first. Okay, so in this problem, what are they telling us? They're telling us we have this 36%, and I'm going to write that as a decimal. Okay, 0.36. What does this equal? Well, it tells us this is our recessive genotype, little a, little a. Notice they're telling me it's my genotype. So if it's my genotype, I can't use my P's and my Q's. I have to use those squared ones. So recessive would end up being my Q squared. So what does that mean? That means, looking up at this equation, if I subtract, if I do 1 minus 0.36, this gives me 0.64. So then I know that from there, my 0.64 is going to equal P squared plus 2PQ. Okay? So I'm just kind of already starting to plug it into this equation a little bit. So looking at the first question, number 1, the frequency of little a genotype would be my 0.36, or my Q squared. The frequency of my A allele, what does that mean? So if this is telling me that this is Q squared, how do I figure out Q? I'm looking for Q by itself. Okay? So if I'm looking for Q by itself, how do I figure that out based on this? Well, it's going to actually be pretty simple. I should know that the square root of Q squared is going to give me my answer. Square root of Q squared. Okay, I'm getting rid of that squared. And I'm actually moving it to the other side. So if I square root 0.36, this actually gives me 0.6, and this equals my Q. Then I want the frequency of my A allele. Frequency of my A allele. So for this one, this is a little different. You actually can't just do this, which is the square root of 0.64. Okay? Some of you might see, oh, well, I had 0.64 left. Well, 0.64 represented p squared plus 2pq. So you can't do it like that. What you actually need to do is figure out that p equals 1 minus q. Okay? And we know that from this above equation. So then, if I know q, then I can go ahead and figure out p. And how do I do that? Well, p is going to equal 1 minus my q, which was 0.6, which equals 0.4 is my p. And the last thing, it says the frequencies of the genotypes AA, homozygous A, and heterozygous. So, the frequencies of those. I know that, well, what do I know? I know that AA, the frequency of AA, is going to be what? If I wanted the frequency of AA, then I actually need 2pq. How do I figure out 2pq? So, I'm sorry. Big A, little a, heterozygous, is equal to 2pq. So when I want to find 2pq, I just really need to plug that in, which equals 2 times my 0.4, which I figured out for p, and my 0.6, which I determined for q, and that should add up to 48. Okay? So then how do I find big A, my frequency of that genotype? Well, in this case, I should be able to just subtract. Okay? So that means that if I don't already have my AA, and AA was p squared, and here I'm looking, I don't have p squared yet. This is p squared. I can just plug it into that equation. So p squared is equal to 1 minus 2pq. I'm moving this over from the other side. Minus q squared. So p squared is equal to 1 minus, my 2pq is 0.48, minus my q squared, which I determined earlier, was 0.6. What did I do wrong? Oh, 0.38. 0.36 minus 0.6. There we go. And so that's going to give me my p squared is going to equal to 0.16. And watch out for my mistake right there. Okay? If I needed to double check, then I could just add 0.16, 0.48, and 0.36 together, and I should add up to 1. And the last thing I want us to look at is a little bit on this Hardy-Weinberg applications. What do we actually use Hardy-Weinberg for? Well, this allows us to predict the occurrence of alleles in a population. And just keep in mind that a population also represents our gene pool. Okay? It's going to determine the percent of genotypical heterozygotes from phenotypical dominance. Genotypic heterozygotes, what is that going to be? That's going to be our 2pq. From our phenotypic dominance were represented by p. So just looking back at the previous equation that I had there. And one thing, however, that it can't determine is that the Hardy-Weinberg can't determine if an individual is heterozygous or homozygous dominant. And obviously this is only going to work for traits that are dominant and recessive. However, we can predict the next generation of the population. One thing I want to mention to you guys is this idea of a heterozygote advantage. The heterozygote advantage is when you have, for example, sickle cell anemia and malaria protection. In this case, if you have enough sickle cells, that actually causes the protist that causes malaria to be unable to live in the cells. So when you're looking at this type of problem or this type of disease, something like NN would represent our increase in the chance of malaria, and SS would represent our sickle cells, individuals that have all sickle cells, and they tend to actually pass away or die. Sickle cell anemia is a co-dominant trait. So this one actually shows us that it's not always the recessive and the dominant trait, but actually we can determine codominant traits as well. And actually almost any trait that has this idea of a heterozygote and a homozygous zygote. But we're going to stop there for today and look at the rest of these Hardy-Weinberg principles in class.